Okay, hello everyone. So today is Saturday. Let's revisit one of the most popular paper in terms of efficient convolution neural networks. EfficientNet rethinking model scaling for convolutional neural networks by Tamizin Quant et al. Published in ICML in 2019. Okay, this paper is mainly about a very comprehensive study on efficient new convolutional neural networks. It's mainly about how we can scale these convolutional neural networks to achieve higher accuracy while using fewer number of parameters. So the main contribution of this one is that, well, first they systematically study model scaling, especially how they can balance a network depth, width, and also resolution. And so and they propose a new scaling method that uniformly scales all dimensions of depth with resolution using a simple yet highly effective compound coefficient. So further, they use NAS to design this baseline. So the main result here is as follows. So they introduced a family of EfficientNet B7, and they achieved an 84.3% top point accuracy, while being 8.4 smaller and 6.1 faster on inference than the best existing convolutional neural networks. So, and this paper summarizes the main contribution. So here, x-axis denotes the number of parameters, while y-axis denotes ImageNet top 1 accuracy. So here we have model size and ImageNet accuracy. And most of the, so in 2019, most of the popular networks lies here, and EfficientNet is in here. So basically here, the top left corner is better because this is because models here achieve high accuracy while has large number of parameters here. Okay, so and then let's go So here's the it's mainly how they scale the model. So right, so let's say this is the base model, and we have different scaling method. So one of them is a width scaling. So width is the number, width here denotes the number of channels here. By width scaling, we increase the number of channels. B means that we only increase the number of channels, we only increase the width. And C is depth scaling, so we increase the number of layers. Then the network goes deeper. And here's the D is the resolution scaling. Here we increase the resolution, and E is mainly their proposed method. So B, C, D, they do scaling independently in only one aspect, such as only in width, only in depth, and only in resolution. While E, so here we scale, this is a compound scaling. So here, model is scaled by width, depth, and resolution simultaneously in all these 3 dimensions with a fixed ratio. Okay, and then so why this one is better? Oh, sorry. Why compound scaling is better for compared to BCD? Well, there's some observations here. Let's give it a go. Let's see. So he because in width, depth, and resolution, there's some relationship among them, and if we only scale one of them, then it just not as not effective as the compound scaling. So there's some relation between network depth and also width and depth. And here, the author claimed that at the time they're the first to empirically quantify this kind of relation among all 3 dimensions of network, width, depth, and resolution. So, for instance, if the input image is bigger, then the network needs more layers. So, which is depth. We need to scale the depth, and then it will also increase the receptive field simultaneously if we go deeper. In some points, some of the activation neurons in deep layers, they correspond to a larger receptive field in the earlier layers. And also, we also need more channels, which is width, in order to capture more fine-grained patterns. So that's why it's best to use compound scaling because of this kind of relationship. Okay, let's go to, and then this in the Reddit world. Well, there's here's mostly the commonly used ConvNet, and here in terms of efficiency, the main thing here is that deep ConvNets are often over parameterized. So parameterized. That's which is basically saying that there are much more parameters than needed to achieve something. For here is mainly for classification. Then we have some model compression way in the literature and so forth to increase the efficiency. In terms of model scaling, and I mean these are just I mean the how people did for model scaling. So here the formula, this one, the problem here is the compound scaling. So we want to maximize the accuracy and then so the formula this as the optimization problem. We want to maximize the accuracy given the so we treat the depth, width, and also resolution as the parameters, and then so like memory that we have some target memory, some target flops, and then here many the here is mainly the representation of the layers, notions of layers, and next the tensor in each layer, such as in terms of height, width, and the number of channels, which is high width, which is the resolution, and the number of channels with the depth, and L is with this. Sorry, number of channels is the width. Width here, and number L is mainly the depth here. So depth goes from 1 to S for this D, and H and W should represent our resolution R here. Then we have 3 scaling dimensions: depth, width, and height. Resolution. And then we show the graph for each one independently. So here, x-axis denotes the flops, which is floating point operations in billions. And then if we scale width, then here we see we see the curve here. There's some elbow here. So if we have a wide network, we have a more number of channels, then we can capture more fine-grained features, and they are easier to train. And also resolution, they have more fine-grained patterns. And higher resolution improve accuracy, but the accuracy gain diminishes for very high resolutions. So scaling any dimension of network of these 3 dimensions improve accuracies, but the accuracy gain diminishes for bigger models. So it's like here, when we scale here, we see faster increase of accuracy, but later the increase just diminish. Similar here, we accuracy increases faster and then diminishes here. So we should increase network depth, and then larger receptor fields can capture more similar features, include more pixels in bigger images. We can also increase network width when the resolution is higher. And so when resolution is higher, we can capture more fine-grained patterns with pixels. And the main thing is that we need to coordinate and balance different scaling dimensions rather than just conventional single dimension scaling. The observation tool, in order to pursue better accuracy and efficiency, it is critical to balance all dimensions of network depth with resolution during net scaling. And they try to arbitrarily balance network width, height, and depth in the literature, but they all require tedious manual tuning. So here is the proposal, which is the compound scaling method. We have depth D equals alpha to the power of phi, and similarly, so we have phi here, and we have alpha, beta, and gamma. They all scaled in the exponential way. Why? That's I actually would like to know why, but I hope someone can answer this question. So here we have flops of the regular resolution, which is proportional to, here's an interesting thing. So D and W squared and R squared. And then, so convolution operations usually dominate the computation cost in ConvNets. And then they use, so they use some grid search and they found this one, alpha to be 1.2, beta to be 1.1, and gamma to be 1.13, so 1.5 to be best. And the scale goes here. So here's the main result for comparing EfficientNet with other popular networks in 2019. and similar accuracies are grouped in together. So here B0 actually achieves 0.7, so it says 77.1%, and the number of parameters is only 5.3 million, while in ResNet 50 is actually 26 million. It's quite small. It's almost 5 times smaller. And similarly here, EfficientNet B1, they achieve 79.1% accuracy, while the number of parameters is 7.8 million. For EfficientNet, we have similar accuracy, but the number of parameters is 23. Okay, and the rest is explaining the other benchmarks in terms of latency and also transfer learning data sets. And you can read the paper. So here's the main thing here. So in order to understand why compound scaling is better than scale by each of the dimension independently. So here, compound scaling is denoted in red, while others are in different colors. So here we see, here's the visualization of class activity map CAM. Here, if the base model, I think the main thing here we are trying to extract features of these this kind of food is donut or some. So anyway, if we go deeper here, wider here, compound scaling, the shape of components is scaling, the activity field and activity pixels match these objects. And similarly here, it looks more, it match the activation in these regions matches this maze compared to other activations independently. Okay, that's the main thing here. So let's see, just to recap, the proposed compound scaling for width, width, depth, and resolution, where width is the number of channels, depth is the number of layers, and resolution is the resolution of input. To do that, they propose scaling in this by this coefficient phi in this exponential form, and then they do lots of experiments to verify this hypothesis. Okay, thank you. So that's it for this week, and we studied this paper for EfficientNet, and next week I think we are going to study another paper in terms of efficiency. Thank you.